Why? Neanderthal bone tools were more durable than early Sapiens equipment. Imagine holding a smooth, dark brown tool carved from the dense rib bone of a red deer in your left hand, and a sharp, delicate stone blade crafted by an early Sapiens hunter in your right hand. You press the stone blade against a thick piece of frozen bison hide and apply heavy pressure. The sharp stone edge chips, cracks, and snaps under the strain. You then take the Neanderthal bone tool, plant your thumb firmly along its polished ridge, and lean your entire body weight into the frozen leather. The bone flexes slightly under immense torque, absorbing the mechanical shock, smoothing the tough hide without tearing the fibers, and remaining completely intact. For over a century, traditional anthropology assumed that Neanderthals were technologically inferior brutes who relied on primitive stone clubs, while modern humans invented sophisticated equipment. Yet when archaeologists analyze the physical durability, mechanical elasticity, and structural engineering of Pleistocene toolkits, a shocking truth emerges. Neanderthal bone tools were built to endure brutal, high-pressure industrial stress that would instantly shatter early Sapiens equipment. How did Neanderthals engineer tools with such extraordinary durability? And why did modern humans trade away long-lasting structural strength in favor of disposable, fast-produced technology? To understand this monumental archaeological mystery, we must first look at a groundbreaking discovery that completely shattered our understanding of prehistoric technology. For decades, textbooks claimed that working bone into specialized, highly polished tools was an advanced cognitive skill unique to modern sapiens who migrated into Europe 40,000 years ago. That condescending narrative collapsed with the excavations at Abri-Périnée and Pêche de la Zay in southwestern France, led by Dr. Marie Soressi, a distinguished paleoanthropologist from Leiden University and the Max Planck Institute for Evolutionary Anthropology. Researchers uncovered specialized bone tools, known as lissoirs or leather smoothing tools, in deep, sealed Neanderthal soil layers dating back 50,000 years. Well before sapiens set foot in Western Europe, a lissoir is not a crude, snapped piece of bone. It is a meticulously crafted instrument made from the flexible rib of a large ungulate, shaped with a smoothed, rounded tip designed specifically to work animal hides. Dr. Soressi's microscopic and chemical analyses proved that Neanderthals were intentionally selecting specific fresh bones for their mechanical properties, creating specialized leatherworking equipment that was far tougher and more resilient than anything sapiens were making at the time. Why was a Neanderthal bone lissoir so much more durable than early sapiens stone and bone gear? The secret lies in the biomechanical physics of fresh bone composition and stress distribution. When modern humans entered Europe, their technological strategy relied heavily on bladelet technology, producing thin, razor-sharp flint blades and delicate bone points. While flint is extremely sharp, it is also incredibly brittle. Flint possesses high hardness but extremely low fracture toughness. When subjected to bending forces or uneven lateral pressure, microcracks propagate rapidly through the crystalline structure of stone, causing immediate catastrophic failure. Bone, by contrast, is a natural composite material engineered by evolution to absorb massive mechanical loads. Bone consists of tough, flexible collagen fibers reinforced with hard mineral crystals of hydroxyapatite. This unique dual structure gives fresh bone high tensile strength and high elasticity. In a landmark study on prehistoric bone technology, Dr. Francesco D'Errico from the University of Bordeaux performed high-resolution micro-CT scanning and mechanical stress testing on ancient bone tools. Dr. D'Errico demonstrated that Neanderthals possessed an intimate, empirical understanding of bone mechanics. They did not harvest old, weathered bones lying on the forest floor, which had lost their organic collagen and become brittle. They harvested fresh rib bones from recent hunts, while the collagen matrix was fully hydrated and elastic. Furthermore, Neanderthals deliberately chose rib bones from large, heavy ungulates like bison and red deer because of their specific structural curvature and cortical thickness. A rib bone naturally possesses a dense outer wall of cortical bone surrounding a spongy, energy-absorbing interior core known as cancellous bone. When a Neanderthal pressed a lissoir against a tough animal hide, the curved outer cortical wall distributed the mechanical stress evenly across the entire length of the tool. while the inner cancellous core absorbed the micro-vibrations and bending torque. To see how this mechanical superiority played out on the ground, let us reconstruct a concrete scene from 48,000 years ago during a freezing, late autumn evening in the Dordogne Valley of southwestern France. Imagine you are sitting near the mouth of a deep limestone cave, wrapped in a thick, heavy bearskin to keep out the biting sub-zero wind. The air smells of wet earth, wood smoke, and rendered animal fat. Beside you, a bright campfire crackles, casting dancing orange light against the stone walls. In front of you lies a massive, stiff hide freshly stripped from a 300-kilogram bison. To turn this stiff, bloody hide into windproof, waterproof clothing that can protect your family through an ice age winter, you must render it soft, flexible, and impermeable to water. This requires an immense amount of physical force. You hold a 7-inch Neanderthal lissoir carved from a fresh bison rib. The tip of the tool is polished smooth as glass from years of continuous friction. You plant the rounded tip against the rough leather, lean forward with your broad chest and heavy shoulder muscles, and drag the tool across the hide with 80 pounds of downward pressure. As you scrape, the lipids and fat molecules inside the skin are forced deep into the microscopic collagen fibers of the hide, making it supple and water-resistant. The bone tool flexes under your massive strength, bending slightly without cracking. The smooth, rounded tip glides across the leather without snagging, puncturing, or tearing the valuable skin. You work for 4 straight hours, applying relentless, heavy torque to the exact same piece of bone. By the end of the night, the hide is soft, supple, and ready to be tailored. You wipe the grease from your lissoir, tuck it safely into a small leather pouch beside your hearth, and smile. That single tool has been used by your family for over 3 years. It has processed dozens of heavy hides, survived hundreds of hours of intense mechanical friction, and remains as strong and polished as the day it was made. It is an industrial-grade, multi-generational heirloom. Now, contrast that scene with a Sapiens campsite located 30 miles down the valley a few thousand years later. Sapiens leatherworkers often relied on sharp flint scrapers or delicate, thin bone awls and needles. When a Sapiens worker applied heavy downward torque to a thin flint scraper against a stiff, frozen bison hide, the brittle stone edge would frequently catch on a tough muscle ligament. With a sharp snap, the flint edge would shatter, sending razor-sharp flakes flying across the camp and tearing a hole straight through the hide. Sapiens workers had to constantly stop, pick up a hammerstone, and spend time resharpening or knapping new stone blades to replace the ones that broke. This brings us to a profound, counterintuitive economic twist that completely redefines how we view technological progress. If Neanderthal bone tools were so much more durable, long-lasting, and mechanically resilient, why did modern sapiens ultimately win the evolutionary race? Why did history favor the species that made fragile, easily broken tools? The answer lies in the fundamental trade-off between durability and manufacturing efficiency. This key insight was illuminated by research from Dr. Shannon McFerrin of the Max Planck Institute for Evolutionary Anthropology. Dr. McFerrin noted that creating a Neanderthal lissoir was an enormous investment of time, physical effort, and specialized raw material selection. Finding the perfect fresh rib bone, carefully grinding down the tip against rough sandstone, and polishing the surface to an industrial finish required hours of dedicated labor. Neanderthals designed their tools like high-end, custom-engineered equipment heavy, expensive to produce, but virtually indestructible under normal use. Sapiens, on the other hand, pioneered the Paleolithic equivalent of mass production and standardized, disposable technology. Sapiens focused on producing standardized flint blades and lightweight, modular bone points that could be produced quickly in large quantities. A Sapiens hunter could sit by a fire and knap 20 sharp flint bladelets in 15 minutes. If one blade broke during a hunt or hide working session, it did not matter. They simply tossed the broken piece aside, pulled a fresh blade from their pouch, and kept working. Sapiens built a throwaway economy optimized for speed, adaptability, and low production costs, whereas Neanderthals built a heavy-duty economy optimized for maximum durability and raw structural strength. When climate conditions in Ice Age Europe became wildly unpredictable, the Sapiens strategy of disposable, Easily replaceable technology proved far more adaptable. If a sapiens group moved into a new territory where large bison ribs were scarce, they could quickly adapt by making dozens of small stone blades from low-quality local river rocks. Neanderthals, bound to their heavy, specialized, resource-intensive equipment, struggled to maintain their high-investment manufacturing style when megafauna populations collapsed and raw materials became hard to find. When you reflect on this ancient technological rivalry in your modern life today, the parallels are striking. Today, we live in a world dominated by the ultimate expression of the sapiens technological strategy. We buy cheap, disposable plastic tools, fast fashion clothes designed to last a single season, and electronic devices meant to be replaced every 2 years. We have traded away durability, craftsmanship, and structural longevity in favor of low cost, mass availability, and rapid replacement. Yet, every time you hold an old, handcrafted wooden tool, a heavy cast iron skillet passed down from your grandparents, or a finely tailored leather jacket that refuses to wear out, you are experiencing the exact same appreciation for durability that kept Neanderthals alive through hundreds of thousands of Ice Age winters. You realize that true engineering excellence is not always about making things cheaper or faster. Sometimes, the pinnacle of human ingenuity is creating a tool so tough, so resilient, and so perfectly balanced that it can withstand the harshest pressures of the world without breaking. You look down at your hands once more, setting your broken plastic scissors on the desk. You take a quiet breath and think back to those broad-shouldered Neanderthal artisans sitting in their limestone caves 45,000 years ago, polishing deer ribs against sandstone by the light of a crackling hearth. You realize that those ancient tools were not primitive artifacts of a forgotten era. They were masterpieces of organic engineering, built by master craftsmen who understood the deep laws of friction, strength, and durability long before modern science was ever born.